Welcome to the class. Dear students, today we are going to see what is saponification number. But before looking at saponification number, we have to answer 4 questions. We have to look at 4 questions and try to answer them. Question number 1, what is a soap molecule? Question number 2, what is the source of soap molecule? Question number 3, how do you prepare soap molecule from that source, and what is this process called as? Question number 4, how does a soap molecule actually act like a soap or act like a detergent? After solving these questions, we will look at what is saponification number, and then we will try to determine saponification number by theoretical determination of saponification number. And lastly, we will look at significance of saponification number. This is part 1 of saponification number. In part 2, we will look at practical determination of saponification number. So without wasting time, let us start. Saponification number. What is a soap? As you can see, a soap is a sodium salt of long chain carboxylic acid, or it is a potassium salt of long chain carboxylic acid. Now, what is a long chain carboxylic acid? I am saying about long chain carboxylic acid, not short chain. So R can be C12 carbon 12 carbon atoms, or R can be 14 carbon atoms of 16, 18, 22, such long chain carbon atoms. I am talking about long chain carboxylic acids. So long chain carboxylic acids are called as fatty acids. So it is, what is a soap? It is a sodium or potassium salt of fatty acids or long chain carboxylic acid. Question number 2, what is the source of a soap? What is the source of soap molecule? The answer is that the source of soap molecule is a triglyceride molecule. It is a triglyceride molecule, this one. It is a fat molecule. The triglyceride molecule is called as a fat molecule. So triglyceride molecules you can find abundantly in animal fat and in vegetable oil. So that is why we can make, using vegetable oil such as a coconut oil, we can make soap. Olive oil, we can make soap, because the component there is a triglyceride molecule, right? Question number 3, how can you make soap from a triglyceride molecule or a fat molecule? The answer to this question is subject it to alkaline hydrolysis. Answer is subject it to alkaline hydrolysis. Now, I used the word hydrolysis. Hydrolysis, what it actually means, it is the addition of water. So when water is added, what would happen? The molecule would get degraded. The molecule would get split. One part of the molecule will get H, this part, and the other part will get OH, this part, right? So as this is alkaline, it will get OK, right? O minus K plus. But the question now here again is, where is the water? Why do we call it hydrolysis? The answer to this question is that we are using ethanolic KOH. So what would happen here, that look at this is ethanol and this is KOH. And what would happen? This H, this OH, right? It would go with this H, and this would combine and become H2O and C2H5O minus K plus. So now water is there, water is produced, so it can go for hydrolysis, right? And alkaline, why do I say it as an alkaline hydrolysis? Because this is sufficiently very basic. This is a very strong base. So it is actually aqueous basic condition that we are carrying the hydrolysis in. So that is why it is called as basic hydrolysis or alkaline hydrolysis. It's very strongly basic. So now we are conducting the alkaline hydrolysis using ethanolic KOH. What would be the outcome? What would be the outcome? If you look at this, this is nothing. This triglyceride molecule is actually a triester of long chain carboxylic acid, correct? So what happens if ester is hydrolyzed? Answer is, when ester is hydrolyzed, it splits into its component alcohol as well as its component acid. So that is why it split it here into its component alcohol, which here is a trihydric alcohol, glycerol, and its component acid, RCOO minus K plus. So that is the soap molecule here. The sodium salt or potassium salt of long chain carboxylic acid is formed in this way. If you are using NaOH here, the result that you will get is a sodium salt of long chain carboxylic acid or a sodium salt of fatty acids. I hope this one is clear. If you are going reverse in this way, that process is called as esterification. That would occur in the presence of catalytic amounts of H2SO4. What I mean to say that if an acid combines with an alcohol in catalytic amounts of dilute H2SO4, this would result. And what we have done here this way, correct? So this is the process of saponification. So we have answered our first question, what is a soap molecule? A soap molecule is, as I said, sodium or potassium salt of fatty acid. Second question was the source, that is a triglyceride molecule. Third question was, how do you do that? You subject it to alkaline hydrolysis and it will split into its component. That's it. So that is a soap molecule. Now the fourth question that lies before us is, how does a molecule like this, how does this molecule, it acts as a soap? That is a question that is to be seen. So let us see that question. For that, what I mean to say that how a molecule like this or a molecule like this acts as a soap. So for this, I take an example of sodium stearate. Sodium stearate, the formula is C17H37CO minus Na plus. Let me draw its structure. CH3, so that is the structure of sodium stearate. Each of this point peak and each of this points are CH2. So if you are counting, there are 17 carbon atom, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 17 carbon atoms are there, 37 hydrogen atoms. This is the structure of sodium stearate. This is a soap molecule. We are going to prove how it acts as a soap molecule. What is the detergent action of the soap? What is the mechanism of action? So if you see it clearly, there it is having two parts. This is the first part, which is non-polar hydrocarbon tail. This is the first part. From here till here, this is the non-polar tail, non-polar hydrocarbon tail. And this part here, this part, this small part is the polar head. This is the polar head. So in our clothes, we have all kinds of dirts. There are water soluble dirts, there is oil soluble dirt. No need to worry about water soluble dirt because it will dissolve itself in water. What about oil soluble dirt? Let us see how it acts on oil soluble dirts. Suppose this is an oil soluble dirt in your cloth, okay, in your shirt or pant. It's an oil soluble dirt. What happens is, our non-polar tails, they get solubilized like this in the grease or dirt, correct? So this is the situation now. The polar heads won't solubilize here. Only the non-polar tails would get solubilized in the greasy part. It gets pegged. It gets pegged into it. Correct? It gets pegged into it, or you can say it gets entangled into it. It gets entangled into it. All of these non-polar tails, they get entangled into it, or it gets pegged into it. Now, if you are putting some pressure, how do you put some pressure? If you are putting pressure by rubbing, okay, with your hands, or by tumbling in the washing machine, or by boiling, what would happen? This greasy dirt, it would get dislodged and it will get split into small oil globules like this. Small oil globules like this. And these oil globules will be pinned. It will be pinned by the non-polar tails. Right? And at the end there will be polar heads. So this would be the situation. So what did I say? I said that the non-polar tails would get entangled into the grease. It would get pegged into the grease. And what would happen if you are putting some pressure like rubbing or tumbling or boiling, it would get dislodged. It would get split into small oil globules that would be spinned into the non-polar tails. Right? Now, as oil globules are hydrophobic, they would try to remain above water. Am I right? As polar tails are hydrophobic, they would try to remain above water. The non-polar tails would also remain above water, partially remain above water, while the polar heads here, they will remain in water. Right? They are solvated in water, so they will remain in the water. Correct? So there is a push and pull kind of situation here. Right? They will remain in the water. Oil globules are atop the water, atop the surface of the water. They are hydrophobic. They will remain above the surface of the water. Right? And the non-polar tails would also try to be above water. However, they will be pulled by polar heads that are solvated in the water. Now what would happen? The question is whether they would combine with each other, whether they would merge with each other, and whether they would go for coalescence. So the answer to this is they would never merge with each other. These oil globules will never combine with each other. They would never merge with each other. They will never go for a phenomena such as coalescence. Okay, why? Because these are polar heads. All these are having like charges. They would repel each other. So therefore they would never merge and never go for coalescence. And therefore a situation like creaming of emulsion would never take place. Creaming is combination of all oil globules to make a big large layer of oil. So that situation would never turn up if you are using a detergent. Okay, so creaming would never take place. So basically it will remain as an oil in water emulsion. It will remain as an oil in water emulsion which can easily be swept away by a stream of water. So that is how, dear students, our molecule, that is sodium or potassium salt of fatty acid, act as a detergent or acts as a soap. Now let us look at what is saponification number. Saponification, we have seen the process of conversion of a triglyceride molecule or a fat molecule into a soap is called as saponification. An example we have seen using general example. Now let us see what is saponification number. So saponification number is the number of the milligram of KOH. I'll come to it. I'll rub this and come to that. Let me rub the heading also. Fine. It is the milligram of KOH that is required to saponify 1 gram of oil or fat. It is a milligram of KOH required to saponify 1 gram of oil or fat, or you can say it is the milligram of KOH that is required to convert 1 gram of fat or oil into soap. Correct? It is a milligram of KOH required to convert 1 gram of oil or fat into soap. That is called as saponification number. So to better understand, we can determine saponification number theoretically. For theoretical determination, we need to know the oil that we have taken. Okay, so we are going to now see how to determine saponification number theoretically. Fine. For theoretical determination, you need two things. Number one, you need to know the oil. When I say you need to know the oil, what I mean to say, you need to know the molecular formula of the oil so that you can calculate the molecular weight. So you need to know the molecular weight of the oil, And number 2, you need to know how much weight you have taken. How much weight of oil or fat is in your hand. These two things, if you know, you can determine saponification number theoretically. For that, you have to know the oil. That is the main thing. And weight, of course, you can take and know. But the main thing is you should know the oil which you have taken. Or you should know the molecular formula. Let us understand this concept better by using an example. So I will take glyceryl tripalmitate as example. Let us try to saponify glyceryl tripalmitate. So here I am going to draw glyceryl tripalmitate. So here I have write CH214 CH3, that is glyceryl tripalmitate 14 CH3. Fine. 14 CH3. I want to saponify glyceryl tripalmitate. This is ethanolic KOH. Okay. Let me go for saponification. What will I get? Of course, you know that I will get the constituent alcohol because it is an ester, and I will get a constituent acid. What is the acid that I get? 3 CH3 CH214 COO minus. This is K plus. Right? So I am getting, I have taken glyceryl tripalmitate and I have subjected it to alkaline hydrolysis. This is an ester. Alkaline hydrolysis of it would mean that it would split into its component alcohol, which is a trihydric alcohol. This is glycerol, and the component acid, which is the palmitate acid, palmitic acid. So this is a potassium salt of palmitic acid or potassium palmitate. So the soap that I have got here is potassium palmitate. Potassium palmitate. Please observe that for every 1 mole of glyceryl tripalmitate or any other triglyceride molecule that I use, 3 moles of KOH is consumed. For every 1 equivalent of, or for every 1 mole or 1 equivalent of triglyceride molecule that we use, 3 equivalents of KOH is being consumed. Please note this point. It is very important point and we will use it when we are saying significance. Fine. So that is, I have saponified glyceryl tripalmitate and I got the soap molecule potassium palmitate. Now let us try to determine theoretically. First I said to you that for knowing theoretical, for having theoretical determination, you need to know the molecular formula for this. So the molecular formula for glyceryl tripalmitate is C51H98O6. Now you need to calculate the molecular weight. So how you get the molecular weight? You know 51, right? You know into 12 plus 98 into 1 plus 6 into 16, right? So how much do you get? The answer to this is 806 gram. 806 gram. So you have used 806 gram, correct? So I am rubbing this and I am writing 806 gram. Okay, 806 gram of glyceryl tripalmitate, right? Fine. Now I have to calculate KOH. How much KOH I have used? So the molecular formula for KOH is 56.1056. 56.1056. So I have used 3 equivalents, right? So that will, so we should multiply it by 3. The answer that we get is 168.3168 gram of KOH, right? So our definition, what is our definition? Milligram of KOH required to saponify 1 gram of oil or fat sample. So we have to convert this into milligram. So we will convert this just multiply it by 1000. What you get? 168,316.8 milligram of KOH. Right? Fine. So I'm going to write that here. That is 806 gram 168,316.8 milligram of KOH. Fine. So that is what is required to make potassium palmitate. Right? That is what is required to make potassium palmitate. How much milligram is required? 168,316.8 milligram of KOH is required to saponify 806 gram of glyceryl tripalmitate. So therefore, for 1 gram, how much will be required? For 1 gram, 168,316.8 divided by the molecular weight of that oil, which is 806. Fine. The answer to this is 208.829 milligram of KOH. So what does it mean? That 208.829 milligram of KOH is required to saponify or to convert 1 gram of GTP, glyceryl tripalmitate, into soap. So for any oil or triglyceride molecule, for any oil molecule, if it is having molecular weight is equal to m, then what will be the saponification value? This thing, correct? What is it? 168,316.8 divided by m. So that will be the saponification of any oil molecule that is having a molecular weight of m. Suppose you are taking an oil molecule or a fat molecule, the molecular weight of which is 205 gram. Then for 1 gram, how would you calculate? Yes, 168,316.8 divided by 205. So you will get the saponification value of that oil. So you need to know, what you need to know, I told you earlier, you need to know one thing and only one thing, that is the molecular weight. That is the molecular weight. Dear students, that is how you calculate saponification value theoretically. Now let us understand the significance of knowing saponification value. What is our benefit? So let us see that. Let us have a look into the significance also. So for determining significance, let me draw the general reaction once again, and also the mathematical formula of knowing the saponification value. So the general reaction is like this, right? That this is a triglyceride molecule. I am drawing it once again to make you understand it better. And we are reacted with 3 KOH. Okay, I want to ask you one thing. Okay, we get alcohol, that's fine, and we get soap molecule. Okay, that is okay. I'm not going to draw all that. I'm going to ask you only one thing. How many KOH is required? 3 KOH is required. 3 equivalent of KOH for 1 equivalent of triglyceride. Correct? I'm asking you, why 3? Because there are 3 ester linkages. There are 3 ester linkages. Okay. Now let me ask you, if you are increasing the chain length, that is, if your R group is more lengthy, would this become 4 or 5? If the R group is more lengthy, would it become 4 or 5? Never. It would never become 4 or 5. It will always remain 3 because it is only dependent on the ester linkages. So what I mean to say is, look at this formula now. What was our formula? S is equal to, that is saponification value, is equal to 168.316, right? 316 divided by 3168 divided by molecular weight. Okay, look at this formula of saponification value. Do you understand anything? Look at this. Do you understand anything? Yes, let me tell you. If you are increasing R, if you are making more lengthy, if you are using a more lengthy chain of fatty acid, what would happen? This would not decrease, this would not increase, neither it would decrease, it will remain constant. The constant value for this is 168.3168 gram. That would be this one, milligram. 168,316.8 milligram. That is a constant weight, right? So this won't be affected, this will remain constant. What is getting affected if you are increasing the chain length? Molecular weight is getting affected. Molecular weight is getting affected. So if you are increasing the chain length, molecular weight will increase and saponification value will decrease. So less saponification value. If the saponification value is low, what does it mean? If the saponification value is low, what does it mean? It means that molecular weight is high. Molecular weight is high. It also means that chain length is lengthy. It's not a short chain. So chain length is lengthy, it's a long chain. So if saponification value is low, molecular weight is high, it means that more lengthy chain is used. And see, it is having inverse relation. And if saponification number is high, what does it mean? That molecular weight is low. It means shorter chain length of fatty acid. Shorter chain length of fatty acid. So what is the benefit of knowing this? Okay, the benefit is we have seen saponification number and we have also seen molecular weight. Of all this, we have categorized this into two. Okay, what is the category according to saponification value? See, saponification number high, what does it mean? Molecular weight is low, chain length is shorter. Chain length shorter. And saponification number low, molecular weight high, chain length longer. Chain length of fatty acid longer. So for making good quality soaps, we need this category. We need oil or triglycerides that are having a high saponification number. That is requiring more number of KOH, more weight of KOH. Correct? So that is one of the benefits. So we want this category for making good quality soaps. Good quality soaps means bathing soaps and soft soaps. Soft soaps means your hand washes, lotions, shampoos, hand washes. So you can make good quality soaps in this category. For this, saponification number should be high, molecular weight should be low, and of course chain length should be shorter. For this category, you can make washing soaps, hard soaps and all. I hope this is clear why we are using saponification number. We are discussing the first significance here. The second significance of knowing the saponification number is you can know, it's very direct and there is no need of applying so much brain into it. You can directly know the milligram of KOH that is required. Correct? Now for saponification number of glyceryl tripalmitate, right? What was the saponification number? 208.829. What does it mean? It means that you require 208.829 milligram of KOH to saponify 1 gram of GTP, glyceryl tripalmitate. So you have come to know before doing the experiment or before application, before making soap, you already know the milligram of KOH that you would want to require. Okay, so that has economic benefits for us in making soap. So that is the second advantage of knowing the saponification number. The third advantage, what is the third advantage? You can know about adulteration. You can know about adulteration. How do you know about adulteration? See, the saponification value of glyceryl tripalmitate, as we have discussed, is 208.829. Fine. If it is if you are doing experiment practically. If you are doing experiment practically, you don't know about the oil, you are doing it practically, and in practical determination, the saponification value you got is more than 208. It is more than 208.829. Okay, if it is more than 208.829, then what does it mean? That it means that it has been adulterated. What it would mean? It has been adulterated with oil that is having, yes, low molecular weight and shorter chain length. Right? The inverse relationship. What I am saying, it gives you an idea on adulteration. Suppose saponification of glyceryl tripalmitate, not suppose, if the glyceryl tripalmitate saponification number we have got 208.829. If we are getting more by practical determination, if you are getting more than 208.829, then it would mean that your oil has been adulterated with another oil having low molecular weight and shorter chain length. If it is less than that, saponification number is less than that, then it would mean that the oil has been adulterated with high molecular weight oil which is having longer chain length. So you can get an idea on the adulteration. This part is very important when the oil involved is very costly. Okay, it's a costly oil. So that part is very important. This adulteration part becomes very important. The fourth advantage of knowing the saponification number is, any guesses? Yes, what we all like. What do we like all? Yes, food. So we can determine the oil used in food, whether it is good quality oil that we have used in food, and what is the quantity of oil that has been used in food. It gives you an idea of food. Also, it gives you an idea on storage, okay, and whether the oil is fit to use. Okay, dear students, I hope you have liked the class. In earlier part, in this part of the video, we have discussed what is a soap molecule, what is the source of a soap molecule, how to make a soap molecule from its source. We have seen the mechanism of cleansing action of a soap. We have seen then the saponification number. We have explained it. We have tried to theoretically determine saponification number. Two things we need to know: the molecular weight of the oil and the weight that we have taken. And finally, we have discussed about the significance of oil. In the second part of the video, we will try to practically determine the saponification number of oil in case we don't know what the oil is, or we don't know the molecular formula of the oil. In that case, we try to practically determine it. That we will see in the second part. Dear students, if you have liked the video, if you have understood the class, please do not forget to subscribe this channel and to like and share it. Thank you very much.